way. All right, so here we have a number of variables that we've worked with before, right? I'm going to open the labels here so we can see this a little bit better. I am recording, yes I am, good. And so let's say analysis of variance. So I'm working with analysis of variance. What kind of comparison am I making? What kind of variables? If I'm dealing with two kinds of variables, what type of variables are those if I'm doing analysis of variance? Right? Well, analysis of variance means that we're going to compare means, right? So we have to have some scalar variable involved. We have a bunch of them here. We have the mother's age in this data set. We have the amount of weight gained by the mother. We have the amount of weight gained by the infant or fetus, or the birth weight of the infant. And that's it. The others are nominal variables. Some of these nominal variables have, for instance, the gender of the infant have two values, right? So some of these nominal variables have more than two values. For instance, the race of the mother, right? That has, in fact, has 8 values, right? Or 9 values, actually, because it includes 0. They're actually going to run into, yeah, I think I might actually do something there because we're going to run into a problem that I know is going to be an issue if we wind up with a data set like that. Okay, so now, how about like smoking status? I think is 2 variables, right? 0 and 1, and so on and so forth. Okay, so we know that if we're dealing with a nominal variable like smoking status and a numerical variable like the birth weight of the infant, then we can use that numerical variable, that categorical variable, smoking status, to divide those values up into 2 groups that we can compare. In other words, we can compare the birth weights of infants from mothers who smoked versus the birth weights of infants whose mothers didn't smoke. And we know that in that case, we'd just be doing a simple t-test, right? So we go to compare means, independent samples t-test, it's not the same mothers. It's not, obviously, they're all individual infants, so it's not the same mother for all the different infants and so on. And so it's going to be independent samples t-test. And in this case, my test variable is going to be my numerical variable. In other words, the weight of the child, I'm going to use ounces just because it's handy. And the grouping variable is going to be whether the mother smoked or not. Now, I took a quick glance over there, and I don't know if I can do this still now, but the 0 was the value for mothers who did not smoke, and 1 was the value for mothers who did smoke. Right, so I know that the groups are defined by the numbers 0 and 1. When I'm doing a t-test, SPSS requires that I identify those groups, what numbers are represented by those groups, because it's possible that in another circumstance, for instance, if I'm looking at if I'm comparing ethnic groups, but I'm only comparing, not all of them, but I only want to compare the race of the mother of one particular ethnic group, right? Like say Chinese to Filipino, I want to compare those two. Well, then I could do a t-test and tell it that the 2 numbers that we want to compare are 4 and 7, and it'll pick out those 2 values, even though there's 8, 9 values for this categorical variable, it'll pick out just those 2 and do a t-test. So I can actually still do a t-test if I just want to limit it to comparing any 2 of these values. So that's why it asks you for the identification of these actual variables. When we work with analysis of variance, it's not going to ask us that. It's going to assume that we want to compare all of the groups within that variable, okay, within that categorical variable. So I'm going to go up to here, and we should be able to set the alpha error, the alpha that we want for this test, the level of certainty that we want for this test before we reject the null hypothesis. And we want to be 95% certain. In other words, we want less than 5% chance of error if we reject the null hypothesis. So if we wanted 1% alpha to be 1%, we would put in 99 here. So I'm going to leave it 95. Okay, and I'm going to click OK. Okay, and it'll come up pretty quick. Okay, let's see. I think I did click it. Yep, here it goes. Okay, you see what we have. First box tells us the number of children in each group, and obviously, since most mothers do not smoke, we had more mothers that were in the non-smoking group than we had in the smoking group. We see a difference in the mean birth weight. Mothers who smoked had smaller babies, lower birth weight babies than mothers who did not smoke. Now, our concern now is we want to decide whether or not that is a significant difference. And with the t-test, we know we have a couple of ways that we're really comparing these two means in terms of the standard errors. Now, SPSS calculated the standard error for this sample of 684 women who didn't smoke, and a standard error for these 114 women who did smoke. So I can see that the standard deviation and the standard errors are different for these two groups, but they're not all that different. Just looking at, remember that the sample size has a lot to do with the standard error. So for right now, in terms of the variability of the values in these two groups, I want to just look at the standard deviation. I don't want to look at the standard error because this is, even if the variability was exactly the same, the larger sample size would make one of these standard errors significantly smaller than the other. So if I look at this, I see standard error here, standard deviation here, and they're very similar. So I say to myself, if they weren't a double, one wasn't double the other, I might just stick with the assumption that the variability is the same in both groups. And we really don't have a reason to question that, right? In other words, even though we think it's reasonable that mothers who smoke might have lower birth weight babies, we don't have a reason to think the variability would be different. Not the mean, but the variability would be different from these mothers who did smoke. So I don't have much reason to assume that, and in fact, it doesn't look like that. I don't see anything here that would suggest I should do that. However, SPSS will actually do a test to check for that, and that's Levine's test for the equality of variances. And if we look here, the statistic for Levine's test is 0.897, and the significance, the probability, the p-value, the probability that you would be wrong if you reject the null hypothesis is 34%. Right? Well, that's pretty high, right? We don't like being wrong more than 5% of the time when we reject the null hypothesis. We don't like that level of probability. Well, in fact, what we're testing is for the equality of variances. Again, we're looking at it as a null hypothesis. So we're assuming that the variances of these two groups are equal. So if this value is not less than 0.05, we can't reject this idea that the variances are equal. So we stick with using the top line here all the way across. Had this significance been less than 0.05, we could reject the idea that there were equal variances, the null hypothesis, and use the bottom line that equal variances are not assumed. Okay, and in fact, if you look at this, if I had done that, and I used the bottom line, my t-test result would have been 3.8 instead of 3.5. I would have had an advantage by using equal variances not assumed, but it would be an unfair advantage in this case because I don't know for certain that equal variances are not true. So I'm gonna use the top line here and go across here, and the t-value is that these two, based on this composite standard error, based on all these values, because we're assuming equal variances, the t-value is 3.1, 3.5. The probability of getting these two values, if they're from the same population, if the means for all the mothers in North Carolina, birth weights for all the infants in North Carolina for mothers who didn't smoke versus mothers who did smoke, if they were equal, right? Well, the probability that would be true, given how far apart these means, how many standard errors apart these means are, is less than 1/10 of 1%. So I can reject my null hypothesis and say, remember, my null hypothesis was that the mean weight for birth weight of infants from mothers who smoke is equal to mean weight for birth mothers who don't smoke, and the alternative was the mean weight for mothers who smoke is not equal to the mean weight for mothers who don't smoke. So I can go across here and I can see I can reject my null hypothesis. And if I look over here, this is the 95% confidence interval of the difference between these two means. And in order to, our null hypothesis is the difference, mu1 minus mu2. The difference is equal to 0. There's no difference between the two means. So what I'm developing a confidence interval here for is to compare it to the value 0, no difference between the two means. And in fact, we're 95% certain that the true mean for the differences between these birth weights is between 3.5 and 12. So since 0 is outside of this confidence range, we're 95% certain that the difference is not 0. In other words, that there really is a difference here. Okay, so that's basically the t-test. The analysis of variance is really at the basis kind of a t-test also. We're going to take a look at that right now. Okay, so I'm going to go over here. And actually, you know what I might do quickly here? Let me see if it'll let me do this. Compare means. I'm going to go here to one-way analysis of variance. And I'm going to put the birth weight of the child into the dependence list. And I'm going to put the smoking status of the mother into the factor list. Now, notice it's going to compare both groups. It's not going to ask me to define them. It doesn't care. It could have been one value, 2 values, or 9 values here. And I'm going to click OK. And it's going to use the same data, and instead of doing a t-test, perform an analysis of variance. You guys may remember how we did that with Excel, where we actually compared the variability within the groups to the variability of the means of the groups, and so on and so forth. Variability between the groups to the variability within the groups. Okay, let's take a look at what we have here. Okay, so let's see, degrees of freedom, analysis of variance between groups, degrees of freedom. The F value is 12.363, and I get the same result for the significance, the probability of being wrong if we reject the null hypothesis that these two are from different populations, that they're different. Okay, so actually, analysis of variance basically will give you a result that mirrors what the t-test would be if you only ran it for 2 groups, in case a question like that comes up. Okay, so now let's actually employ the analysis of variance. I'm going to employ it in a situation where I know I'm going to run into a problem ahead of time. You may not have tried this yet, but just in case it happens for you, I'm going to go in here to one-way analysis of variance, and I'm going to stick with the weight of the child. I'm going to move this factor out. Now, anybody want to propose a categorical variable here that has more than 2 values? So I can compare 3 groups for their means, or 4 or 5 or whatever. Anybody want to? What would be any appropriate categorical variable here that would work for us? Has more than 2 values in that group. Ethnicity and race. Okay, great. Okay, let's go down there. Ethnicity and race. I'm going to move that into the factor group. Doesn't ask me. It's going to do it for all the groups with all the values within that group. I'm going to go in here and say I'm going to turn off post-hoc tests. I don't want that on yet. And I'm going to click OK. Okay, I'm just going to run right now my analysis of variance. Is there a difference in the means for any of the groups within the ethnicities? Okay, let's take a look at what our result is. Our result this time is an F value. Now let's take a look at this. The F value here is 8.222. That's the value of the chi-square statistic. And that we would go to a table to look up what the probability would be for the number of degrees of freedom that we're dealing with. So let's take a look at how this is determined. Well, first, we found the sum of the squares between the groups. Remember, between each of the means, there's 8 groups here, right? Or maybe there's not 8 groups. Let's see. How many groups do we have? We have degrees of freedom, ethnicity. I think there were 8 groups. I'm not sure why it's saying 3. 796. So we got 8 groups. Did I pick the right one? Did I pick the right variable here? Did I pick ethnicity? Oh, did I pick? Yeah, hang on a second. Let me go back and see what I picked. Oh, you know, I'm in the output table. This is variance, ethnicity. Let me just go back in here. Oh, race of the mother. Okay, and what was the other variable here? Was there an ethnicity variable here also? Yeah, here it is. Ah, that must have been a special. The reason why I only saw 3 degrees of freedom is because there were 4 values minus 1. Number of groups, the number of values minus 1 would have been 3 degrees of freedom. So the only values I really actually I meant to. Hang on a second here. I got ahead of myself here. I outsmarted myself. I'm going to go back here and try it again for the race of the mother. And a couple of you guys have already noticed what I did by mistake there. I'm going to do this now. Okay, race of the mother. Now there's 8 values here. Okay, wait for it to come up. Okay, it calculates it for me, and it does the analysis for me, and between groups, and so on and so forth. And let's see. Actually, I was thinking. Okay, so it appears that there are that we are dealing with 6 groups, and that our significance, our probability that that all of the means are equal, our null hypothesis, is very low. It's less than 1/10 of 1%. Okay, so I'm going to go ahead and run a post-hoc test now to try and determine which of the values might be different, which of the racial groups might have different average birth weights. So I'm going to go back up here to, again, I got to go to Analyze, Compare Means, One-Way Analysis of Variance. This time I'm going to run a post-hoc test. Hopefully on the test they'll suggest which ones you use. So usually Tukey or Bonferroni. I'll pick Bonferroni. I'll click Continue, and I'll say OK. And now SPSS. Now that I've determined that at least 2 of the means are different, I rejected my null hypothesis. I'm going to go ahead and run a post-hoc test, trying to identify which of the groups are different. Well, I got a problem here. Post-hoc tests are not performed for the weighted child because at least one group has fewer than 2 cases, has an insufficient number of cases. Well, if I go back and look at the data, what I'm going to notice is, let me go to the data view. What I'm going to notice is that under the race of the mother, that there, oh, was it the race of the mother? Yes. Under the race of the mother, that if I sort by this, then I'm going to find that one of the groups at least could be, say, American Indian or Asian Pacific Islander or something like that. One of those groups has too few values to run this test. Okay, so what's a good way for me to get around that? Well, if the groups I'm really interested are, say, white, black, let's see, let's say white, black, and what do we have? What other group do we have a number of? Asia Pacific Islander. Actually, let me do it this way. Analyze descriptive statistics frequencies. Let's take a look at the frequencies for race of the mother. Might as well take advantage of this, right? Since it's here anyway. We'll find out the frequencies for each of the people in that group, for each of the ethnic groups within that variable. Can't see which one of these was the problem. Here we go. These Chinese and Filipino were the 2 groups that had too few values for us to do the analysis. So I do have enough white, black, American Indian, and Asian Pacific Islander. So now let's eliminate these 2 ethnic groups so we can at least perform this analysis of variance on the 4 remaining ones. So one way I might do that is I might go up here to transform, and I'm going to create a new variable. Okay, and I'm going to, I could compute a new variable. I can recode into a different variable, recode into the same variable, in other words, change the variable. I could recode into a new variable, I could compute a variable, in other words, do a mathematical operation on it. I'm just going to create a new variable from the variable that I already have. So I'm going to click on that. I get a window that comes up and asks me, what's the variable I'm going to start with, and what's the variable I want to end up with? Well, the variable I'm going to start with is the race of the mother. I'm going to move that into that box there. And the variable I'm going to create, the variable I want to create is the ethnicity. Let's see, race of, how about this? For group race. Okay, call that the name of the variable. I could create a label for it. I don't think I really need to right now. But now I can go in here and I can tell it the old and the new values that I want to have. So if I go back here, I'm going to cancel here. Whoops. Well, let me hit cancel. Let's see if I can get back to, so, okay. So go to variable view. Nah, I can't do that. No, I gotta have to say cancel for a second right now. The reason I have to say cancel is I have to get back to the variable view because I forgot what the various values were. Race and mother, variable view. Okay, so the values that I want are white, 1, 2, 1, 2, 3, and what was the last one? Anyway, I'm just going to do 1, 2, and 3. Okay, those three groups. The first 1, 2, and 3. Okay, so I'm going to create a new variable with only those three groups. Okay, transform, recode into different variables. I'm going to go back here again to race of the mother, and I'm going to say new variable is 3 group 3 value race. Okay, and I'm going to say old and new values. Okay, so the old value was 1. The value in the new variable is going to be 1 as well. Okay, I'm going to add it. The old value was 2. Value in the new variable is going to be 2. Okay, oops, forgot to add it. Okay, the old value was 3. The new value is going to be equal to 3. So now, if I add this and I click continue, okay, we've told it that we want to create a new variable called 3-value race that only has that is based on the original variable race of the mother and only has the values that are 1, 2, and 3 recreated in the new variable. Okay, so I'm going to go over here and say, go ahead and change it, make this new variable, and then say OK. And if I look back now, in a second, group several together to create, yes, it is, as a matter of fact. One of the things that, that's a good question. One of the things I could have done, for instance, if I wanted to combine Asian Pacific Islander and Filipino and so on and so forth, I could have, when I recoded in the old and new values, I could have said, okay, make the value number 4, make 4 equal to value 4. And then I could say make 5 equal to value 4. So now whoever was in group 4 got identified as 4 in the original variable, or 5 in the original variable, is both of those are combined into group 4. And for instance, 6 could have been 4 also. Okay, so I'm not going to do that right now, but that would work also, and then combine them into a single variable. That's a good way for you on your project, for instance. If you have a variable that says, categorical variable, that says the amount of sugary drinks that people drank, and the values of the groups are, you have 4 groups, let's say. First group is less than 2 a week or less than 2 a month. And the second group is 3 to 7. And the third group is 8 to 10, 8 to 20. And the fourth group is 18, 20 to 21 to 30 or something like that. And you don't want it to condense that into 2 groups. You can make the first 2 groups 1 and 2, you can combine them into a single variable 1, and then you could take the higher two groups and combine them into a single variable 2. Okay, I don't think you'll need to know how to recode for the exam. It might come in handy for the project because again, I just was able to recode, like a little bit of soda, almost no soda, a little bit of soda, quite a bit of soda, and really a lot of soda into two variables: a little bit of soda, a lot of soda, so that you could do odds ratio with something that originally started with 4 values. You got it down to 2, and you could do odds ratio with that. Okay, which would help you out chi-square and odds ratio a little bit more comfortably. But you're right. You guys are right. I probably shouldn't spend too much time on this since we're concerned about the exam. So thanks for putting me back on target. So I'm going to say, okay, here. Actually, I think I might have already done that. Okay. Yeah, I did get it. So you notice, yeah, it's done already. So I'm going to close this. I don't need to do this anymore. Cancel. Okay, you'll notice now if I go back to my variable view, there's a new variable there called 3-value race. And if I look at that in my data view, you'll notice that it has values 1, 2, and 3. And where the other values existed before, for instance, right here, that was other Asian or Pacific Islander, right? That didn't get carried over to the new data set now. So all we got now is 1, 2s, and 3s. So now I can go into analyze. I'm not going to code it and say compare means, analysis of variable, work with this new variable I created instead. And oops, put it in the wrong place. I meant the weight. That was the weight of the child. Work with the new variable, and now I will be able to do that analysis. I got post-hoc turned on. Yes, I do. I'll go through the whole thing at once. Okay, so now, since we eliminated those other two variables, there actually is a lot of ways to skin a cat here. There's other ways you could have filtered these variables, filtered those values, and so on. So this time, we didn't get that message that it was unable to perform the post-hoc test, because some groups had 2 view variables. It was actually able to do it, and we could compare group 1 to group 2, and so on and so forth, to see which ones were significantly different. And group 1 and group 2 are significantly different. The others are not. So I think that was white and black, I think. I'm not positive, but that's my recollection. I could have coded it and made it a little bit more simple. So we're able to reject the null hypothesis that all the means are the same, because we ran the analysis of variance, and then we were able to identify which of the groups are significantly different, 1 and 2 in this case, but not 2 and 3, and not 3 and 1 or 3 and 2 are not significantly different. Okay, so we're able to identify those by you doing the post-hoc test. Okay, so that's analysis of variance. Now let's take a look at chi-square. Okay, so chi-square, we're normally concerned with categorical variables when we work with chi-square. Okay, because we're actually doing an analysis that's based on contingency tables, right? Or tables that summarize categorical values into columns and rows. Okay, so in the rows, we usually like to put, say, an exposure or something that we think is a causal variable, and the outcome variable or the result in the column. So, for instance, exposure might be in the rows, and whether or not there's disease might be in the columns. Okay, so I'm gonna start with we want to work with variables that are categorical variables. So we have gender as a categorical variable, has only 2 values, right? And we have, well, mother's age is numerical. How about, let's see, that's the sex of obviously not the sex of the mother, that's the gender of the infant. So that's not all that interesting right now. That's probably pretty random, right? It's almost random. I think it's 50%, a little bit more than 50% would be females in most populations. Okay, but we got marital status. What is marital status? Well, there's 2 values, married or not married. Okay, well, that's interesting. What do we think might affect marital status? What might marital status affect? Maybe it'll affect whether or not the infant is born prematurely. Okay, infant was 0, infant was not premature, and 1 infant was premature. So that's pretty interesting. Let's see if there's something here like smoking or drinking during pregnancy or the marital status that might affect the likelihood of a premature birth. Or in this case, this one is low birth weight, I think. Kind of same thing. 0 was the infant was not low birth weight. 1, the child was low birth weight. And the other one, premature, if it was not premature, it's pretty much the same variable, isn't it? Okay, they might have divided this up somehow or other differently. If we didn't have that variable, we could create that variable by taking the weight of the child and transforming or computing a new variable based on the weight of the child, where we define as under a certain number of ounces, the child is premature, or over a certain, I'm sorry, premature is different than low birth weight, isn't it? Okay, the weight, let's say the weight at low and normal birth weight could be based on the weight of the child being under a certain amount or over a certain amount. Okay, and we could do that by saying, oh, well, take a look at the ounces birth weight and assign this in the new variable of value 1 if the birth weight is over a certain number of grams. Okay, and so on. So let's take a look at this in terms of doing a chi-square analysis. So I'm going to look at, just for the hell of it, whether or not smoking status has some impact on the premature births. Okay, so I'm going to go up here to analyze, and in this case, let's see. I want to be in. This is kind of a descriptive statistics, right? Because really what we're doing is we're just organizing this data into frequency tables, right? So I'm going to go into descriptive statistics and crosstabs. So you're not going to see chi-square right away, I would hazard, right? You're just going to see crosstabs. So in the rows, I want my exposure. So in this case, my exposure might be whether or not the mother smoked during pregnancy. And that's going to be a 0 and a 1 kind of situation. In my columns is going to be whether or not the infant was a low birth weight infant. And I'm going to move that into my columns. That's the outcome. Okay, so before we do anything else, I'm going to make sure statistics is turned off here. There's nothing turned on there. I'm going to go into cells, and I'm going to ask it to just calculate one thing, the observed values. Just organize this data into a table for me. Okay, so I'm going to click continue and click OK. Okay, here it comes. And it's done exactly that. The rows are mother did not smoke during pregnancy, mother did smoke during pregnancy, and the columns was infant was not low birth weight, the infant was low birth weight. So you'll notice that it adds up to 798. There was a couple of pieces of missing data in here, I would guess. I think it started with 800. No, it only started with 798, I guess. Okay, so you'll notice that, but if you're doing this on your own, a couple of these NC birth 800 or whatever modified NC birth files might have been tinkered with before. So this one has only 798 rather than 800 subjects. So at any rate, so I'm looking at this, I'm saying, okay, well, there were 684 mothers who did not smoke. The great majority of them did not have a low birth weight baby, 629 versus 55. While the majority of mothers who did smoke also did not have a low birth weight baby, right? Most of them had normal weight babies. But now I want to take a closer look at that. You know, those numbers, they're informative, but they're really kind of hard to interpret. So I'm going to go up here to analyze to, where is it? I have to be in analyze, descriptive statistics crosstabs, except this time I'm going to go into cells and I'm going to ask it to calculate the percentages by rows in addition to the observed values. Okay. Boop, boop, boop. Let's go. Okay, any day now. Here we go. Okay, so notice same numbers, nothing's changed, 629.55. Except this time it calculated what the percentage of that particular group, mothers who did not smoke, what percentage of them were not low birth weight. Well, looks like 92%, only 8% were low birth weight babies. 92% were not low birth weight babies. Mothers who did not smoke during pregnancy, 86% were not low birth weight, 13.2% were low birth weight babies. Well, that's interesting because it looks like there's a higher rate of low birth weight babies among mothers who smoked rather than mothers who did not smoke. Okay, so now how am I going to evaluate this information? How am I going to analyze whether or not that difference is really is due to chance, or if that difference is really due to a difference in whether in the populations of mothers who did smoke versus mothers who didn't smoke? How am I going to evaluate that? Well, I need to work with a statistic that'll figure that out for me. Well, one of the things that I can do is I can create two tables. One table is my actual observed values. Okay, if I look at this overall, down in this bottom row, overall for everybody, there were whether they smoked or didn't smoke, there were 728 babies that were normal birth weight, and there were only 70 that were not low birth weight. So 8.8% for this entire sample population, 8.8% was the rate of low birth weights, right? So if I went back here and looked at this, and I looked at these 684 people, right, I would expect 8.8% of these people to have low birth weight babies. Okay, and I can actually just multiply 684 times 0.088, right, and I'll get a number. That's going to be my expected value. Instead of 55 low birth weight babies, I might have expected like 60. Instead of 8%, I would have expected 8.8. So this is less than I would have expected to see. Okay, over here, let's see, 13.2%. That's more than I would have expected to see. You can actually ask SPSS to calculate that that estimated value table for you. I'm going to go into, up again, I have to be in the data file. Descriptive statistics, crosstabs, kind of hidden there, remember, keep that in mind. Cells. This time, I'm gonna ask it to show the expected values also. Now, SPSS, a little inconveniently for us, is going to actually, it's kind of handy if you're doing a report because you only have to put one table and have all the values. But inconveniently, if you really want to demonstrate this, like right now, it'll put the expected counts into the same boxes, right? In fact, look, it's exactly 60. We would have expected 60 low birth weight infants among mothers who didn't smoke if the rate were the same in both populations. And we would have expected 10 instead of 15 among mothers who did smoke. These are the expected values. These are the observed values. In fact, in Excel, when we did this in Excel, we actually made two separate tables. Now, my statistic, my chi-square statistic, is calculated by comparing the observed values to the expected values for each one of these different boxes. Okay, in Excel, we actually did that. We took the difference between the two values here, the observed and expected for each of these four boxes. We squared the difference. We divided it by the expected value, and that gave us a number. And we added that to the number for the next box and the next box and the next box. We added all those numbers together, and then we went to a table that gave us a critical value for chi-square given the number of degrees of freedom that we have. That would be the value that we would have to exceed for the chi-square statistic, the sum of all those four numbers, in order to reject the null hypothesis. Was that their null hypothesis is that there is no association between smoking and birth weight. Okay, so I would have to exceed that critical value. Now I would have to go to a table, but I'd have to know the degrees of freedom. Anybody want to hazard a guess? What's the number of degrees of freedom for this 2x2 table? Anybody remember how to calculate that? Come on, somebody. What's the degrees of freedom here? Yeah, it's actually n minus 1. It's the number of rows minus 1 times the number of columns minus 1. So it's 2 rows, so that's 2 minus 1 is 1, times number of columns of minus 1 is 2 minus 1 is 1. So 1 times 1, 1 degree of freedom. So if I went to the table for a critical chi-square value for 95%, we would see, we would look under degrees of freedom equals 1. So actually with SPSS, I don't need to do that. I can go to Analyze. Come on, let me get this. Analyze, Descriptive Statistics, crosstabs, and I can go into the Statistics and ask it to calculate the chi-square value for me. And it'll do that calculation just as we did in Excel and give me a table back. Okay, and I'll wait for it. Okay, so let's see what we have now. So our chi-square value, is 3.197, which represents I don't know if you guys remember, but from the table when we were working with this in class, the critical value that we need for 1 degree of freedom to with an alpha of 5% to reject the null hypothesis is 3.8. So this number is smaller than the critical value. So as expected, my p-value or significance is bigger than 0.05. So in this case, the difference is not great enough for me to say with 95% certainty or 5% chance, less than 5% chance of being wrong, that there is an association between smoking and birth weight. That it would have been possible that the difference is due to chance rather than real difference in the two populations, right? So I failed to reject the null hypothesis. Now we can also, while we're here, I'm going to go back. Now, the continuity correction, I don't think you're going to have to worry about that for the test. You're subtracting another 0.5 from each one of those numbers before you square it. So it makes it a little bit, it's a more conservative approach. In this case, both of them wind up rejecting the null hypothesis, failing to reject the null hypothesis. So I'm going to go back again to my data. I'm going to say Analyze, Descriptive Statistics, except this time I'm going to ask it to do something else. I'm going to say, let's go into here to Cells, and Cells, and I'm going to turn off this expected values and percentages by row. No, I'll leave percentages by rows on. Okay, but I'm going to go back here into Statistics, and to the chi-square value, I'm going to ask it to calculate risk as well. Okay, and I'm going to click Continue. It's now going to calculate the risk for a mother that smokes having a baby that's low birth weight. We actually already have that. That's in the percentages by rows. The risk might be 8% for one group, might be 10 point something for the other group. Okay, but it's also going to calculate something called the odds ratio. So just by clicking off risk there, I'm going to click OK, and it's going to do the calculations and bring up the output for me. Come on. Here we go. Okay, so here we go. So here is our table just as before. I just uncluttered it by getting rid of the estimated values. You'll see that there's an 8% chance that mothers, or risk, that mothers that didn't smoke would have a low birth weight baby. And there's a 13% chance that mothers who did smoke during pregnancy would have a low birth weight baby. Right? There's actually this, I guess the sample size is a little bit too low for us to have proven that this was association. This was a real association, not just due to chance. We missed by a little. Actually, we came really close, right? 0.07 is pretty close to 0.05, so we came really close. So I'm encouraged that maybe there is an association, but I wasn't able to reject the null hypothesis. So now we haven't proved. In fact, remember, we just say we failed to reject the null hypothesis, which means that this result doesn't prove that there's no association, right? It just says that we weren't successful at proving that there was an association. Okay, so let's go here and take a look at it. Here's our chi-square again, and continuity correction just as it was calculated before. But down here at this other table, I have another estimate. It's called a odds ratio. So let's take a look at this. The odds of having a baby if the mother smoked during pregnancy is 13.2%. And the odds if she didn't smoke during pregnancy is 8%. Well, 13% divided by 8%, the risk, not odds, I'm sorry, the risk of having a low birth weight baby is 13% versus a risk of 8%. So the risk ratio is 13% to 8%. It's almost they're almost twice as likely to have a low birth weight baby if the mother smoked during pregnancy. Actually, not quite twice as much, maybe 1.6, does it look like? 1.6 and 1.7 times as much. Well, in fact, if you go down here, here is our, where is it now? Actually, the way that this displays it here is it actually, this is our, it's actually 0.611. Actually, I'll describe this. Because uh, uh, the not low birth weight was in the right column, and the mother's not smoking was in here rather than the other way around. We can actually change these values. So smoking, mothers who smoked was the 0, and this was the 1, so it would be the reverse, and this was the reverse as well. But what the real ratio it's calculating is the 0.8 to the 13.2, 0.8 over 13.2, and that's our risk ratio, and it's 0.611. So a woman that does not smoke is 0.611 or 60% as likely to have a low birth weight baby as a mother who did smoke. Her risk was reduced by that much. Okay. However, if we had done it the other way around, we would have gotten a number that was something like 1.2, 1.7 or something like that, 1.6 or something like that. And that would have suggested that her risk was 1.7 times as great. A little bit more intuitive, but it's really the same number in a sense. Okay, so now what about the risk? What about the odds ratio? Well, the odds ratio is based on the number of women that had low birth weight babies versus didn't have low birth weight babies. In other words, 629 over 55 versus mothers who did not smoke during pregnancy, 99 over 15. The odds here are 99 over 15 or something like 4.5 to 1, I guess, 5, a little bit more, 6 to 1. The odds here are like 12 to 1. So it would be 12 to 1 over 6 to 1 or 12 over 6. And that would wind up with a odds ratio of 1.7. Women who did not smoke during pregnancy were 1.7 times as likely to have a normal weight birth weight baby. As opposed to mothers who did smoke during pregnancy. You know, it's a little bit makes it a little bit difficult to interpret when we have this so that the positive exposure smoking is in the bottom row rather than the top row, and the outcome that we're looking for that we don't want, or the disease, is in the right column versus the left column. And we can correct that by recoding this so that the zeros and ones are reversed for each of these two, or we can just keep that in mind when we read our result table. And I know that it's a little hard to interpret. Maybe it's good that we saw this, because maybe if something comes up where the variable, where the data set that you wind up working with on the exam has kind of a twist like this, that you realize that by looking at this, that you have to be a little bit careful with the way you interpret the risk. Okay, and worst comes to worst, you can always just do your own calculation here for risk ratio by saying, oh, this is 15 out of 114 or 13.2%, and I'm going to divide that by what's the risk if they didn't smoke. 55 out of 844, 8%, 13.2 over 8 is going to be a relative risk of whatever it came out to. Okay, and you can actually calculate that yourself. That's the inverse of this 0.611. Okay, now the important thing here is that what is the value that you would expect for the odds ratio or the risk ratio if there was no difference in the risk or the odds for smoking or not smoking? What would you expect that risk ratio or that odds ratio to be? What number? Would it be 0? Would it be 10? Would it be, what do you think? Somebody? What would you expect that number to be? For no association, right? Not zero. You're thinking about you're thinking about the one exactly. You're thinking right about zero because that's really for the for regression and for correlation and regression, right? No, odds ratio wouldn't be zero because zero when you divide one thing by another thing, not likely you're going to get something that's zero, but it's going to be one. In other words, the odds for women. Think about this: the odds for women who smoked, and the odds for women who did not smoke, if they're the same, the ratio, the top of the equation would be the same as the bottom. So that would be equal to one. Okay. All right. So we're looking for it to be equal to one if there's no difference, but we want to prove that there is a difference. Okay. So if I look at this, let's see, the confidence interval for the odds ratio is, we think it's 1.7. The confidence interval is 0.94 to 3.186. Can I say that it's not one with 95% certainty? No, it can't say that because one is included in the confidence interval. In order for me to say with 95% confidence that it's outside of the confidence interval, that the odds are different for these two groups, it has to be outside of the confidence interval. One has to be outside of the confidence interval. That's not the case here. So just like before, where I was unsuccessful with chi-square, I'm also unsuccessful in proving that there's an association between smoking and low birth weight, because the one is within the confidence interval here. I can't say that this value is really different than one. You know, it's close, right? But I can't say with 95% certainty. That's the value that I think it is, but I'm 95% certain that the true value for the entire population is between these two numbers. And since one is between those two numbers, I can't say with 95% certainty that it's really different than one. Okay, so that's what I have to do with risk ratio. Okay, so just on Sunday we'll get into um, regression and correlation, and just so that we know what we're going to be dealing with there, the kinds of variables that we're interested in there are going to be for the most part. We're not talking about logistic regression, just linear regression, multiple regression for the moment. Okay, the variables that we're going to be dealing with there are going to be two numerical variables. For instance, the mother's age, the weight of the infant. Let's just take a quick look, see if there's an association between those before we sign off tonight. So I'm going to go up to graph. First thing you want to do whenever you do a regression is that you want to look at how this information is distributed. So I'm going to go down here to legacy dialogues because it's simple, scatter dot. Now I'm going to take two of these. I'm going to say a simple scatter dot graph. And it doesn't matter which one I call X and which one is going to call Y right now because I'm working with correlation. And I'm going to look at the age of the mother. I'll put that in the X-axis. How does that affect how does that correlate with the weight of the weight gain during, with the weight of the child? Okay, see if there's an association, whether or not older mothers have have lower weight babies, lower birth weight or higher birth weight. I'm going to go ahead and click OK. You guys think there's going to be an association there? We have time to discuss it while SPSS grinds and cranks here before it comes up. I'm thinking it might be, right? But let's actually take a look here. Well, boy, it doesn't look very good, does it? Right? It looks like there's almost a straight horizontal line. There's a lot of outliers here, right? The weight of the child, these are premature births. So it isn't very normally distributed. It doesn't look like there's much of an association here, does it? Okay, so now the way I would mathematically try and determine whether or not there was a correlation, an association between the age of the mother and the weight of the child is to do a correlation. Analyze. Let's see, here, that. Analyze, correlation, bivariate. There's two variables, so it's called bivariate. And I'm going to tell it, let's take a look at, as before, the age of the mother and the weight of the child. Okay, and I'm going to go ahead and calculate that. And what we're looking for here is a Pearson's chi-square value.
It's 10 o'clock.
A Pearson's value for correlation. It's called rho, like a small r. Hang on a second, let me show you what it might look like. Something like this, right? In other words, lowercase rho, whoops, like kind of like an R, okay, something like that. Rho, if there's no association between these two, then rho is equal to 0. Okay, if there's a perfect association, then rho, Pearson's correlation, is equal to 1. So our null hypothesis is rho is equal to 0. Our alternative hypothesis, that means that there is no association between them. Our alternative hypothesis is that there is an association between age of the mother and the birth weight, is rho is equal to, is not equal to 0. It's equal to something different than 0. And the closer that rho is to 1, the greater the association, the more that closely associated the age of the mother and the birth weight of the baby is. Well, let's take a look at this. My null hypothesis was rho is equal to 0, right? So let's see. My Pearson's correlation is 0.168, right? It repeats it down here as well, right? Just does it both ways. Compares weight of the child to the weight of the age of the mother, 0.168, and it compares the age of the mother to the weight of the child. So it does it twice, but it gets the same number always. So is 0.168 a strong or a weak correlation? And we're keeping in mind the idea of the 0 and 1. Is that a strong correlation or a weak correlation? It's pretty weak correlation. However, is that weak association, is it real? In other words, is rho equal to 0 or not? Can I say with 95% certainty that rho is not equal to 0? In other words, it may be small, but not equal to 0. There is some small association between the weight of the age of the mother and the birth weight of the child. Okay, and keep in mind that if this is a positive number, rho, it means that it slopes upwards. In other words, as the age of the mother goes up, the birth weight of the child goes up. And if it's a negative correlation, as the age of the mother goes up, the birth weight of the baby goes down. So in this case, it's a positive correlation. It's a plus, right? So can I say that, can I reject the null hypothesis that there's no association between age of the mother and the birth weight? In other words, rho is equal to 0. Can I reject that null hypothesis and say there is an association? Okay, I got one opinion says no. Where would I look here to decide what's the probability that this value is different than 0? In other words, reject the null hypothesis. I need a probability. I need a significance, right? Well, what's the significance that's calculated? Oh, look, it's less than 0.05. So even though it's a weak association, I have so much data here, right? And even though it's a very weak association, I can say there is a little bit of an association between the age of the mother and the weight of the child. It's not a very big association. In other words, the age of the mother only has a tiny influence on the weight of the child. In fact, I'm going to do something real quick before we end right now. So I can reject the null hypothesis. I can say there isn't I reject the null hypothesis, rho is equal to 0. I can say rho is not equal to 0. In fact, it looks like it's equal to 0.168. But I can reject the null hypothesis that there's no association and say there is a slight association. But now what I can do also is I can go in here and I can actually calculate something called R squared, rho squared, right? I can do that a couple of ways. I'm not going to go into regression right here, although I could. I'm just going to double click on here and ask SPSS to do the best it can to fit a line to this data, right? A best fit line to this data. It's going to do it for me. And while it does it, it actually calculates. See that line slopes upwards a very small amount. It actually tells me that R squared is equal to 0.028. In other words, if I took my R value and squared it, it came out to 0.028. You know what that tells us? That R squared value tells us that about 2.8, about 3% of the value of the weight of the child can be attributed to the age of the mother. So 3% of the change as we go up in age of the weight of the child is influenced by the age of the mother. Well, that means that 97% is influenced by other factors: the amount the mother gained during weight, the gestational period, the other conditions, and so on and so forth. So even though we've shown that there's an association, I can reject the null hypothesis, there is an association. That association is really, really weak. It's not really very significant. There are other things that are much more relevant, even though the age of the mother has some relevance to the weight of the child, and we prove that with 95% certainty. There are other associations that are stronger, that are that have more influence in determining the weight of the child. I'm guessing the number of weeks of gestation is going to be a big one, right? Let's just see that on a graph if we can, and then call it a night. We'll come back and do this again on Sunday. Graph. Like I say, oh, by the way, I noticed that Professor Weicker posted the article that she's going to ask questions about on Blackboard for the exam. So you guys might want to go on there and make sure you get a good start, get an early start on that, get a chance to read it. Okay, and let me see here. Instead of age of the mother, let me see. Do we have completed weeks of gestation? I think that's this. Yep. Okay. Weeks of gestation. I think that's really going to have an influence, right? So I'm going to click OK. Let's see what our chart looks like there. And see if there is a more significant association, a more clinically significant association. Not statistically, but clinically. Can't see what that, oh, well, wow, look at that, right? Weeks of gestation is clearly associated with the weight of the child, right? And in fact, if I take a look, do an R value there, okay, the R value, I don't have it here. I'd have to go in there, but R squared is equal to 30.34. So it must have been 0.6. Must have been around the R value must have been around 0.6. R squared is 0.34. So 34% of the change in the birth weight of the child is associated with the weeks of gestation at birth. That is an enormously more important clinically than the age of the mother, right? So even though I could prove that there's an association with age, it's not as important as the association with weeks of gestation.